Hello everyone. Today I'm going to start with the electricity topic in OCR. You can see from the specification things I have on the screen that we have first charge. So the first topic that they start with in OCR is charge. So basically how charge behaves. It has a whole chapter to itself, so chapter 8. So these are the learning objectives for chapter 8. And I will go on to link it to the other chapters as well. So to start with, it's very important to understand what an electric current is. We have seen that electric current is the rate of flow of charge and is given by the equation shown. So you can see that I stands for the current. Q or change in Q, so the delta sign, capital Greek letter delta, means change in, and Q stands for charge. So Q is a symbol for charge, and the unit of charge is measured in coulombs. Delta T is for the change in time, and is measured in seconds. Current has a unit of amperes, and it's a capital A. Charge has a unit of coulombs and is a capital C. They're named after scientists, hence why they need to be capital, whereas time in seconds doesn't need to be in capital, it has to be in lowercase. And you also need to be able to define ampere as a unit, is one of the requirements. 1 ampere is 1 coulomb of charge passing a given point per second. It's quite easy to define a quantity with quantities only, and units with units of the quantities only. So that would be very useful to use. So if you were to define 12 kiloamps, for example, you should already know what the unit prefixes are. So that is times 10 to the power of 3. So that means we have 12,000 amps. And therefore I could say that 12,000 amps is when 12,000 coulombs of charge pass a point per second. So yeah, I put a note here for you to remember that you could be asked to define these words. So current is a quantity, amperes is a unit, so you need to define quantities with quantities and units with units. Now, going back to the very, very basics, we know that every single object is made up of atoms, and atoms have a nucleus that you can see here as the positive protons with the neutrons in the nucleus and surrounded by electrons, which are negatively charged. So we already know that in nature, everything has a positive and a negative charge. But since the two charges are usually balanced, there's no overall net charge. So positive and negative charges cause a neutral object. So all atoms are neutral unless they're ions. The electric charge is measured in coulombs, and we call the elementary charge the smallest unit of charge that you can have. This was measured using Millikan's experiment. I will go into more depth into it when we learn about electric fields and magnetic fields and so on. So I'll go into more detail later on about that in later chapters, in A2 chapters. Now the elementary charge is considered to be 1.6 times 10 to the minus 19 coulombs. Now this is a direct physical property of a material, like matter is a physical property, so mass. They've measured it through experimental ways, through Millikan's experiment to begin with, and then Millikan discovered that every single charged object has a multiple of this, an integer multiple of this number of the elementary charge. We usually use a symbol to show it. It's just E. To represent the elementary charge, which is the charge of a single electron or the charge of a single proton is the number. Obviously, you need to consider the sign. So if it's a positively overall charge, so electrons were removed from a substance, then it will have an overall positive multiple integer of the elementary charge. or if it's a negatively charged object, so it gained electrons, then it will have a negative multiple integer of elementary charge. You used to do that in chemistry. You used to see it as this ion, for example, Na minus, which means it has an overall -1 charge. That means its overall charge is minus 1.6 times 10 to the minus 19 coulombs. Sorry, positive. My bad. Chlorine, on the other hand, will be minus 1.6 times 10 to the minus 19 coulombs. So, for example, if we have magnesium 2 plus, that will mean that its overall charge is plus 2 times 1.6 times 10 to the minus 19 coulombs, which is 3.2 times 10 to the minus 19 coulombs. So you can see clearly that any multiple of the elementary charge is the overall charge of an atom or an object, depending on what we're looking at. We only know of 2 charges that exist, positive, negative, and obviously neutral is not considered as a charge, but we should mention it here. The fact that protons are positively charged, electrons are negatively charged is something that you have seen throughout your chemistry and physics GCSE course. Now, if you want to calculate the net charge of an object, you need to know, for example, the number of electrons added or removed, and then multiplied by the elementary charge, just like we did in the examples above. As I said already, charge is quantized, so you can only have integer multiples of the elementary charge. There cannot be a charge that's, for example, 0.9 times 10 to the minus 19 coulombs. This does not exist. It has to be a multiple of 1.6 times 10 to the minus 19. That's the smallest charge measured. So when we say quantize, we mean that it's a fixed value and you can only get multiples of it. There's a nice question here. Once again, we always treat questions in a way that we look at them as a little mystery to solve, and we also make sure that our units are correct and what equations we will need to use. It's a good point to mention that this equation is not given to you, but it's based on ratio. So if you have one electron or one overall electron added or removed in an object, then it will be 1 times that electron and so on. This is the current through a lamp is this much. So we have the current, calculate the number of electrons. So I need to find n passing through 1 point in the lamp in 2 minutes. So that's my time. And I need to change my time into seconds. So 2 minutes is 120 seconds. Always need to keep it to standard units as the first thing you do when you read a question. And you need to find the number of electrons. Now, there's no equation that I have seen so far. So I have 2 equations. But none of them directly give me the number of electrons. So it means I have to do some rearranging and substituting to be able to calculate the number of electrons. The idea that we have I, we have T, means that will give us Q. And if we have Q, this is a constant. So I already have that number. So once I calculate Q, I can find the number of electrons. Now, the only issue with this is you can substitute it inside or you can do it step by step. I prefer to do the substitution because it keeps all the numbers together, and then I put in the numbers or the symbols together, and then I put in the numbers to give me less calculations to do on my calculator. So I will go on and rearrange for Q. And then I will place Q in this equation. So that will be IT is equal to NE. And I will rearrange for N now because that's what I need to calculate. So I have N is equal to IT over E. I divide both sides, obviously, to get N by itself since it's multiplied by E. And I just put my numbers in. 6.2 times 120 divided by 1.6 times 10 to the minus 19. And this gives me 4.65 times 10 to the 21. Sorry. Electrons. There is no unit because electrons the number of electrons do not have a unit, so be careful with that one. Also, make sure that the number makes sense. So if you get something negative, you can't have a 0 point. So if you go, for example, 4.3 times 10 to the minus 3, that means that you have 0.0043 electrons, which is impossible because you can't split an electron. So if you get a negative value for the number of electrons as a power, make sure that you do have a look back at your calculations. Maybe you forgot to put brackets here in the calculator when you're dividing. So please make sure you're using the calculators right. So that's one way of calculating the number of electrons if you're just given certain values. So far we have looked at electric current as the rate of flow of charge. I will say what this part is very important in a minute. Coulomb as the unit of charge, elementary charge, and what it is, net charge on a particle as is quantized or a multiple of E, and current as the movement of electrons. So these are the things that we're going to have a look at now, because you do need to know about the electrolytes as well. So why do we define electric current as the rate of flow of charge instead of just the rate of flow of electrons? Will be explained now. So in a metal wire, if we assume that this is a metal wire around, so this bit is all a metal wire with a battery here, then we can see the internal structure of the wire. So what we have is we have our positively charged nucleuses that are fixed in a position. So it's a fixed metallic structure. And they don't move, so the positive ions are fixed there. They have no movement at all. Now, if this circuit was not connected, so there was no energy flowing around, then the electrons will also be quite stable. They wouldn't be moving that much. They wouldn't have any current flowing. But once you apply a potential difference across the wire, you have the electrons start moving. Now, the electrons that are shown here are just delocalized electrons. So not all electrons that belong to an atom are delocalized. Most of them are tightly held by the nucleus, but some of them that are quite far from the nucleus, they get shielded by the other electrons, and hence they don't get attracted too strongly to the positive nucleus, which allows them to move freely. So this is the basic structure. You should be able to describe the basic structure in a metal and what kind of charges move within the metal. So in the case of metals, electrons are the charges that are moving, and that's what causes an electric current. You also need to be able to state how positive ions are fixed. But if you do increase the temperature of the wire, so you have high resistance, for example, then the positively charged nucleuses, ions in the wire will start vibrating more in the same position, which will increase resistance. So electrons will have a net movement when the potential difference is applied across the wire. And if I want to increase the current, I can either increase the number of electrons passing a point per second, or I can make the electrons move, the same number of electrons move faster in the wire. So here I left little thing, that's electron, and that's a positive ion / nucleus, because it is the nucleus of the atoms that make up the wire. Another important point to mention here before I move on to electrolytes is the difference between conventional current and electron flow. It's very, very important because we do use it later on when I start doing the video about capacitors. You should not get that mixed up, and it's usually questioned as well in terms of how you connect diodes. Is very important. So we have a battery, has the positive and the negative terminal. Now in this case, we know that conventional current is something that they have defined before they discovered that electrons were the ones actually moving. And I think due to the reason that everything was defined based on positive charges moving, it remained. So conventional current is from positive to negative. Electron flow, though, is in which direction electrons actually do flow. Now we know negative charged particles repel, and positive and negative charged particles attract. That means that the negatively charged electrons will flow from the negative side all the way to the positive because they're attracted to the positive terminal. So that defines electron flow. So you need to be able to identify these points. Another important part before I also move on is how do we measure current? So to measure current in a circuit, you have to connect an ammeter in series with the components that you're measuring. And one of the biggest questions is, what should the actual resistance of the ammeter be? So if I have a light bulb there and I want to measure the current flowing through the light bulb, I have to place an ammeter in series with the component. Now, remember that ammeters, voltmeters, they are measuring devices that should not be taking part in your measurement. Like a ruler that shouldn't affect your results. An ammeter shouldn't either. So the best, since an ammeter measures the number of the charge passing per second through the circuit, it shouldn't have any resistance. So an ideal ammeter should have 0 resistance. Otherwise, it will decrease the overall current through the circuit and will measure less current actually flowing into the light bulb, through the light bulb. So it's very important to get an ammeter with as low resistance as possible. It's impossible to be 0 because obviously every single component has some form of resistance, but an ideal one would be 0 resistance. So why electric current is defined as the rate of flow of charge. Now we said in the metal wire, the flow of charge is the electrons. In the case of charged particles, though, electrons are not the only charged particles. Ions are also charged particles. So if you have a liquid, for example, specifically an electrolyte, which is an ionic solution, then you have ions. They're not electrons, they're just charged particles. That means we have chlorine, for example, that gained an electron, sodium that lost an electron. That means that they are both charged in this case. So we have a few features that you should be able to label clearly in a diagram. The anode, which is positively charged, and the cathode, which is negatively charged. I find it easy to remember one side and then the other. Now, what's attracted to the anode is called the anions. And what's attracted to the cathode are the cations. If I remember anode, then I remember that anions go to it. And I know that obviously the other one is the opposite, is the cathode, with cations being attracted. If the anode is positive, then the anions are negatively charged particles, and cations, since they're attracted to positive, are negative. They are positively charged ions. So it's an easy way of remembering in that way. It makes it very simple for me. Now, once the anions go to the anode, they drop off an electron. They give an electron to the anode, which is attracted to the positive terminal. And when the sodium cations go to the cathode, they collect an electron and become neutral. So you can clearly see that the ions are moving, which are charged particles, which means that there is a current flowing. So now we have talked about current as a movement of electrons in metals and the movement of ions in electrolytes, and how conventional current and electron flow are. Now, obviously, you can see from the learning outcomes that it's not clear how much you need to know, but I will do an example question later to show the application, so they expect you to be able to apply this knowledge. Kirchoff's first law and conservation of charge is a very, very, very important part of electricity. It actually will help you solve most of your problems in electric circuits, and is very, very, very important. So I'll go on to the law. As a general rule, conservation laws state that a particular quantity does not change. Charge is one of the fundamental physical quantities that are conserved, like mass. So I cannot create or destroy mass, and I cannot create or destroy charge. So the total charge before and after should be the same. And conservation of charge basically states that it can either be, electric charge cannot be destroyed or created, and the total amount of charge, electric charge in the universe, is constant. Now, how does this fit into Kirchhoff's first law? Now, Kirchhoff said that at any point in an electrical circuit, the sum of the currents into that point is equal to the sum of the currents out of that point. In other words, that if you have a million electrons passing a point in 1 second, then going into that point in 1 second, then a million electrons will be exiting that point in 1 second. That's a very important part, because that's what current is, or ions, for example. We will also see this applied later on, but I just wanted to zoom in a little bit into the symbols here. Now, this is a capital Greek letter sigma. It means sum of. And then obviously I stands for current. And the subscript in, so sum of current in is equal to the sum of currents out. If you are to use symbols in your definition, you have to define the symbols. So it's just easier to write that. I also highlighted the sum. It's red because many of you miss that out, and you miss out the whole mark for the definition. Now, how is this law linked to conservation of charge? Well, we said if we have a million coulombs, for example, passing into a point in 1 second, then a million coulombs worth of charge will be exiting that point of the circuit. So you don't destroy charge at any point. Now, if we want to write in terms of charge carriers, the charge carriers entering a point at a given time must equal to the total number of charge carriers leaving that same point during that time. The last part of chapter 8 is about the mean drift velocity of charge carriers. Before we go on to that, we need to first look at what number density is. It's a new quantity that you will need to differentiate from the number of electrons, because they have the same symbol. So the number density is the number of free charge carriers per unit volume. So if a metal or a semiconductor or an insulator, if we measure the number density of them, we'll notice a big difference. So if you have a high number density in a metal, a specific metal, for example, it will mean that you have a high number of free charge carriers per unit volume. That means it makes it a better conductor, right? Because you have more free electrons or free ions to move per second. So we usually show this with the symbol N. And since it's the number of free charge carriers, so number density is the number of free charge carriers. This doesn't have a unit because we're just counting basically how many electrons or how many ions are per unit volume. That means the unit for number density should be meters per meters cubed, basically. We also use this number density to classify materials into 3 different groups. So metals will have the highest number density, so 10 to the power of 28 is a usual number. Semiconductors will have a value closer to 10 to the power of 17, 18. So they have a lower number density, but we can do things to change that, and we'll talk about it later. And then you have insulators that have a very low number density because they don't have as many free charge carriers. So what do we even care about mean drift velocity of charge carriers. Now we know that once we turn the switch on, it lights up the room immediately. So the light comes on instantly. The same thing with some of your phones and reactions to certain features. Now, that's not because the electrons are really, really fast in a wire. They're actually really, really slow. That's the reason they're slow is because as they're passing through the positive ions, they're constantly colliding with them, the positive ions and other electrons. That means that their motion is not in a straight line. So if I had, for example, positive and negative here, then my electrons had to go around the wire, they wouldn't move straight away in a straight path. They would actually zigzag a lot until they go from one end to the other. It's the collective movement of all of them that we consider. And that's where the drift comes in. So they're drifting overall together. And mean is like their average speed that they have. So velocity, don't forget, is speed with direction. So mean drift velocity is basically how fast are the charge carriers moving in a wire, basically. Now, we need to know the equation for it. So we have the equation for current that links it to the speed of, or the mean drift velocity of the electrons. Now, I stands for current, once again, measured in amps. Area is the cross-sectional area of the conductor. So basically the cross-sectional area the electrons actually are passing through. So if we have, for example, a rectangular piece of material, then the electrons, if the current is in this way, then our cross-sectional area is here, because the electrons are passing through that area. Same thing with a wire. We don't take any other area but the area the electrons are passing through. So be careful with that. That's a trick that they usually try and put you off questions. So then we have E, the elementary charge. So that's a constant. You don't need anything for that. It's just a constant already in the equation. N is the number density. Once again, please do not confuse this with the equation we saw before, the quantization. So here N stands for the number of electrons. Here it stands for the number of free charge carriers or number of free electrons per unit volume. And V stands for the mean drift velocity of the charge carriers. So basically the speed, and that's meters per second. Now we can show that this equation is homogeneous with respect to base units. We usually use square brackets to show the units. So here we have, for current, we have amps. For area, cross-sectional area, we know is meters squared. N is the number density, so it's the number of free electrons per unit volume, which is m to the minus 3. E is the elementary charge, so its charge is in coulombs, and then the speed, mean drift velocity, which is the squared. Now I can already see that I have meters squared per meters cubed and meters. Now meters squared times meters is meters cubed, which cancels out with m to the minus 3. So I end with amperes is equal to coulombs per second. We also know that current is Q over T, which means coulombs per second. So that means coulombs per second is equal to coulombs per second. And here I just proved that both sides match. Just remember that now we have two equations for current. The first one is to actually calculate the current. The second one gives us the opportunity to calculate the speed of the average, the mean drift velocity or speed of the electrons or charge carriers within a specific fixed area. The second part I wanted to talk about, which is constantly asked in different ways and in different topics, is how this equation can be used. So it says describe the effect on the mean drift velocity if all other factors are constant and A, current increases. So here it's telling me I need to use this equation to figure out how other factors will be affected, how wind drift velocity will be affected if I change one of the specific factors. So let's do the first one. Since I want to figure out how the mean drift velocity changes, I will rearrange and make mean drift velocity the subject of the equation. So we have NEV. Now, since everything is multiplied, I need to divide both sides by this so that V can stay by itself. So then we have I over A and E. So if the current increases and everything else remains the same, that means that velocity will also increase to accommodate for it, because velocity is directly proportional to current if everything else is conserved. It remains the same, sorry. Then what will happen to mean drift velocity if I decrease the cross-sectional area? And if I look at, again, the equation, just delete this bit. So once again, I have V is equal to I over A and E. That means if I decrease the cross-sectional area, so I'm dividing the expression by a lower denominator, that means I will have a higher velocity. So velocity increases, and the number, then for C, the number density doubles. Now I have, in this case, I was not told increase or decrease, I was told a specific quantity by which it changes. That means if it doubles, I need to give the same, the fraction by which it increases or decreases accordingly. Once again, I have the same equation. So if the number density doubles, that means my velocity halves, because now I am multiplying both sides by a half. So now doing a very quick check, talked about Kirchhoff's first law, how it's linked to conservation of charge. We've seen mean drift velocity. Remember, mean drift velocity is simply the speed that they're moving overall, because they don't have a clear straightaway path. They're drifting. And then the equation, where n is the number density, that's why it's very important and mentioned separately, and how you can distinct between conductors, semiconductors, and insulators in terms of n. So we've already seen that bit. We'll do some exam practice now, and I hope you find this useful. So let's do some practice with Chapter 8 questions that were in the most recent exams. So the first question says a copper wire is connected across a cell. The electrons within the copper move. Which statement is correct about these electrons? So the first one says the electrons drift towards the negative end of the cell. We know that's not true, because we have actually seen that electrons are negative, so they get attracted to the positive. The electrons have random speeds because of collisions with many electrons. It's not because of the collisions with many electrons, it's because of the collisions with many positive ions in the wire that are fixed. C, the electrons travel through the copper at the speed of light. That's definitely not true. There's so many obstacles around for them to do so. In another circumstance, we'll see that they can. And for D, the electrons collide with vibrating copper ions. That's correct. So my answer is D. So when you look at these questions, you should always eliminate the ones that you're sure are not the right answer. So you work with eliminating and then making sure that your answer is correct. Question 2 is an application of, it's a straight question of Kirchhoff's law. It says a diagram shows the conventional currents entering and leaving a current. So it's talking about conventional currents. A reminder that is from positive to negative. We always label in a diagram conventional current. When you're asked to label the current, you always label the positive to negative. So they labeled them as I1, I2, I3, and I4. They are all positive, meaning that they're showing you the direction in which they're moving. And Even though they don't have numbers, it could have been, for example, 1, 2, 3, 4, whatever. They could have had their own numbers, but it gives you a general term, I1. So the subscript just shows you that's a different number. So it says which statement is always true. So if we have a look, we know that the ones going into the junction is I1 and I3. And the ones coming out of the junction are I2 and I4. Now let's have a look. I1 plus I2, that's impossible because if I take I1 on this side, it will become negative. So the first one's wrong. Then the second one says I1. So this is a general expression, by the way, using sum of currents in is equal to the sum of currents out of the junction. So I just wrote the general expression using the law. And you can rearrange it to see if it matches these options here. Now the first one, we said A is wrong. Now I'm going to rearrange and see if my expression here looks like this expression. So I1 minus I2, because I'm taking I2 to this side, it becomes negative. Remember, we're doing the reverse action each time to rearrange. So if I'm adding, I'm subtracting. If I'm multiplying, I'm dividing. In this case, I will only deal with positive and negative since that's the only actions I'm taking. Then it's plus I3. And then since I'm taking this to this side, so minus I4 is equal to 0. And that actually matches B perfectly. Now, I'll always double check. We don't know if I1 is equal to I2, and we don't know if I3 is equal to I4, so that's not correct. It could have been in different ratios. And this is definitely wrong because I'm saying that I'm adding currents into a circuit and I'm getting 0 in return. Now for question 3, I'm going to ignore the first part because this is what we're going to look at later in the next video. It says a chemical cell is connected across a resistor. The resistor is cylindrical in shape, so I'm going straight here. The resistor is cylindrical in shape, meaning that it's got a cylinder shape. Its cross-sectional area, so I know its area is 1.2 times 10 to the minus 6 meters squared. Once again, don't forget, this is a question, so you need to look at the clues within the question and list them, write them down. It will make it much more simpler for you. You also know the length, which is 6.0 times 10 to the minus 3 meters. In this resistor, there are 9.6 times 10 to the 16 free electrons. So I'm going to, instead of writing N, I'm going to write the number of electrons as that. Because I don't know if I need to use Q yet. Q is equal to NE. Or, which is different, this N is different from, which is different to this N, which is a number density. So I need to make sure that I am aware of that already. Calculate the mean drift velocity. So yeah, I will be working with this since I want to know the mean drift velocity. So this is not going to be any use for me right now. So I need to calculate the mean drift velocity of the electrons when the current in the resistor is 3 milliamps. So I know the current too. I'm going to straight away write it down in the standard units. So I need to find the mean drift velocity. I'm just simply going to rearrange my equation and then see what I need for it. Now this is a constant. Cross-sectional area I do have the current, but I do not have the number density fully. I have the number of electrons, I have area and length. So I can literally use it to find the volume. So I can use area and length to find volume, because in a cylinder, if you have the cross-sectional area and the length of the cylinder, if you multiply them together, you get the volume. And since mean drift velocity is a number of free electrons per unit volume, then I can use these numbers together. So my N in reality, I'll have to use all three to get N. So N will be 9.6 times 10 to the 16 divided by 1.2 times 10 to the minus 6 times 6 times 10 to the minus 3. And that should give me the value of n. Now, I would prefer to do this separate instead of putting in the equation, because otherwise it might get a bit mixed up. It's easy to do, it's just don't mix yourselves up if it involves fractions and you're not feeling secure with it. Okay, so that will give us 1.3 times 10 to the 25 per meters cubed. So I have so many electrons for each meter cubed. Now I'm just going to simply place my values in. So this, you can see here why this is 3 marks now. Otherwise, it's usually 2 marks when it's straightforward, or even a mark usually. You have to do some conversions of units, so like milliamps. You have to figure out that the number of free electrons is not the mean density, and you just need to rearrange and plug the numbers in. So we have 3 times 10 to the minus 3 divided by the cross-sectional area times the number density times E. That should give me about 1.2 times 10 to the minus 3 meters per second. Now that's a logical number. We said already that they're colliding so much that they're drifting very slowly, and this value makes sense. So it shouldn't be something extremely huge. It shouldn't be anywhere near the speed of light, and it should definitely not be a really high number. So it makes sense that it could cover about a centimeter or less, a millimeter each second, basically. Which is a logical number. Another way of double checking whether your working out is correct. Now we have this diagram. It's multiple choice again. It says shows the motion of positive and negative particles in a conducting solution. So we have here an electrolyte. Which statement is correct? The current in the solution is 0. That's not correct, because you have current flowing, you have ions flowing. It doesn't make it 0. Since you have positive and negative ions. And don't forget, when you do talk about electrolytes in actual written questions, you have to mention cations, anions, which electrode they go towards, and so on. So the first one's wrong. Need to cross that out. The conventional current is to the left, meaning in this direction, which is correct, because you have from positive to negative. Let's double check the other ones either way. So the positive particles are always protons. That's not correct. They could have been simply positive ions, so charged atoms are positively charged, that lost an electron or 2 or 3. And the negative particles are always electrons. Once again, not true. As you can have negatively charged atoms. So that will be B. Go to the next question. Figure 24 shows a battery connected across a negative temperature coefficient thermistor. The battery has electromotive force and a negligible internal resistance. The ammeter has negligible resistance, so we're ignoring the resistance of the ammeter, and the voltmeter has a very large resistance, which I'll discuss later on. It says a thermistor has a resistance, so it gives us the resistance of the thermistor. It's a good point to mention here, if you don't remember already, that thermistors are semiconductors, so this is a good point to mention that. So when the thermistor has a resistance of 100 ohms at room temperature in a cross-sectional area, so we know the cross-sectional area here, the number density of free electrons, so we know the number density, gives it to us, so I don't have to do any complicated calculations. And it says calculate the mean drift velocity of the free electrons in the thermistor. We know once again that this is the equation I will be using, and it's more straightforward, hence why 2 marks. However, there's something here I didn't mention before, but you should remember this equation from your GCSEs. Resistance is equal to the potential difference divided by the current. So that's another equation that we'll come across. I just thought this question was more useful here now than later. So for me to be able to calculate current, so in other words this, so current is voltage over resistance. Since the voltage all goes to the thermistor, the voltage across these 2 points is 3.0 volts, so there is no internal resistance either, it says, no, negligible, so I'm ignoring internal resistance, so I think all the potential difference, all the energy per unit charge goes to the thermistor, and hence I can calculate the current in that way. So my current in this case will be 3 divided by 100, which is 0.03 amps. And just simply again place the values in. Don't forget any of the powers, because that's a common mistake too, and then you tend to lose all the marks. That's why it's useful to write it exactly like I'm doing. You're showing all your values, how you're putting them in, that you didn't make any mistake around them, and that will be fine with that. That way you can avoid losing too many marks. And the elementary charge, and you should get about 9.9 times 10 to the minus 4 meters per second. This is a question from an A2 paper, so it has some quantities that you don't need to know about. So we're going to start with just looking through it and calculating what we do need. So you have a small thin rectangular slice of semiconducting material with thickness A, thickness B, and it carries a current of I. The current is due to the movement of electrons. Each electron has a charge minus E and mean drift velocity V. Then this part here is not needed for us right now, this part, because you haven't looked at magnetic field yet, which will be later on. It says here are some data for the slice in particular experiment. So it tells you the number density. It doesn't even mention, it says the number of electrons per cubic meter. It doesn't say number density, so that's why you need to make sure you know the definition. So this is N already given. Since I know that I is equal to N E V, then I need to find the mean drift velocity. So I have N. I have current I, so that's given to me too, but I need to change it into amps. So I have E because that's a constant number, and then I am concerned with only the area, the cross-sectional area I need to consider. Since the current is passing in this direction, it shows it to you, the cross-sectional area the electrons are passing through is this. So I need A and B only to get the cross-sectional area. So I'll have to multiply these two values. Once again, change them into meters. It has to be in meters. And then you just place your numbers in. So it will be, this one will be A times B. And we have 60 times 10 to the minus 3 divided by 5 times 10 to the minus 3 times 0.2 times 10 to the minus 3 times N. Once you place the numbers in, you should get 3.1 meters per second. Not that fast, once again, so that's a very good approximation to it as well. This is another great question that pops up quite often. It says the current at the point in the circuit is 10 milliamps, so I is 10 times 10 to the minus 3 amps. Please be careful with it, yeah? Expressed to the nearest power of 10. So, nearest power of 10, very important. How many electrons pass the point in 10 seconds? So my time is 10 seconds. Already I know that I is equal to Q over T and Q is equal to NE. So I just simply rearrange, substitute back in there. So I T over E is equal to N. Therefore I have 10 times 10 to the minus 3 times 10 seconds divided by 1.6 times 10 to the minus 19. Now this gives me 6.25 times 10 to the 17. So looking at the answers, I need to find the nearest power, so I can express it to the nearest power. Our number is over 5, so we can round it to 10, so it can be the closest 10 to the 18, because if that's approximated as a 10 times 10 to the 17, that can be rewritten as 1 times 10 to the 18. And remember, it's like adding zeros to the number. So C is the correct answer here. And then we go to the next question. 8. Which electrical quantity has SI units ampere seconds? Now this is very important. If you look at electrical quantities, you don't talk about units usually in terms of the SI units, but you need to get accustomed to it. So here it mentions ampere second, so you definitely know that you have I times T. Now, which expression reminds you this is I is equal to Q over T, which is Q is equal to IT. So the quantity given by those units is charge. So it should be A. It's not current, because current units are only amps. Resistance, we'll go through it later. Potential difference is V. Even though it's ohms, it doesn't have to do anything with amps and seconds. So sometimes it's better to work the other way around. So what quantity is amps is current, what quantity is seconds is time. And then you figure out through that way. This is the last bit for this chapter for now. Obviously, I will do more questions later on that involve more things of electricity. It shows a circuit that consists of a battery of EMF, 45 volts, no internal resistance, and it has 3 resistors. It tells you the resistance of each resistor, and also it tells you the current that goes through resistor 1 and resistor 2. Then it says calculate the current I in the 750 resistor here. And it's only for 1 mark. So that means that you don't need any excessive calculations. You just need to use Kirchhoff's first law. So you have current entering this junction here is 0.03. Now, some of the current goes in this direction. So that's so we know the sum of currents going in a junction should be equal to sum of currents coming out of the junction. So 0.03 is equal to 0.01 plus the number that goes through this resistor. So that will be 0.02. So the total current in a junction is equal to the total current out of a junction.